Hello, and welcome to my demo on Temporal Set Inversion. Temporal Set Inversion is a method for updating animated implicit surfaces more efficiently over time. And instead of recomputing the entire scene every frame, it tracks how much the scene can change over a short time span and then only updates regions where that change exceeds a threshold. This allows us to skip work in areas that remain stable. Now, here is my OpenGL implementation of the original paper, which was done in WebGL. In this OpenGL implementation, I have two modes for reference. The legacy mode, which uses legacy search tracing as a baseline, and then the TSI pipeline, which uses temporal set inversion. As we can see, both have the same visual results, but they differ in how the scene is updated. The legacy mode evaluates the signed distance field everywhere each frame, while TSI maintains a voxel structure and updates it incrementally. Now we have this flag to show red in areas of the frame that are being updated. So with the current mode, which is the TSI mode, but it's selective, so it means it doesn't visit every voxel or frame. We can see the red is appearing in places where the motion is occurring, and in the more static surfaces, there is not much change. And then in the TSI mode that visits every voxel, the change also applies more frequently and in every frame. Now, in our selective mode, you can see this bursts behavior, and that's because the selective updates aren't always smooth. When a voxel's variation exceeds the threshold, it gets subdivided into smaller voxels, and those children are pushed into the next frame's queue, which can cause bursts in process voxels and GPU time. Another metric that's important here is epsilon, and that controls how much variation we allow inside a voxel before refining. So at lower values, it leads to more subdivision and higher costs, and at a higher epsilon, it reduces refinements, so the animation can get faster. Then with delta, it sets the minimum voxel size to prevent infinite subdivision. And a lower delta allows finer detail, while higher delta stops refinement earlier. And then we have the grid size, and it controls how densely we sample inside each voxel to estimate variation. Higher values give tighter estimates but increase computation per voxel, and lower values give more space in the estimates. So in this paper, it's done with interval bounds, but here I approximate it using sampling. Now we can pause the animation and begin. So the red overlay in this implementation is just a debug visualization. The surface itself is still rendered using ray tracing. So overall, this demonstrates how temporal coherence can localize work and reduce per frame computation.